Okay, so we are here to behavior of the cross section. So depends upon the cross section, behavior of cross section. We can analyze the or we can see the ideal elastic plastic material behavior for the bending purpose. Then again, in the behavior of cross section, we can seek the relationship between the applied movement and rotation. It means what? When your member under loading condition, at that time the behavior of your member changes due to movement and rotation. Whatever movement coming in this particular member, and at what amount of rotation takes place of that particular member. So depends upon that your relation of movement and rotation. It means movement curvature relation is a very important for the analyzing of the analyzing the plastic behavior of this particular member. So now if we take the one of the example of any cross section for the analysis, plastic analysis. So now consider an arbitrary cross section with a vertical plane of symmetry. If you see here, one of the cross section is given, which is also plane of loading. It means that cross section is under the loading. Then consider cross section subject to increasing bending moment and assess stresses at each stage. Now we have to assess the stresses of this particular cross section under the loading condition. So if you see here, CG of this particular member, that means this is the elastic neutral axis. When your member under loading condition, at that time this Y is the vertical axis and this Z is the elastic neutral axis, and here the CG of this particular member. Now, so this is the your behavior of this cross section, what we have taken as an example. So here, if we see here, this cross section, ENA elastic neutral axis and PNA is the plastic neutral axis. So how these two neutral axis shown here? So elastic neutral axis is applied or is up to the behavior of elastic. It means up to the yield point, whatever behavior takes place by the structural steel member, for that the elastic analysis is shown in this above line, and in below line plastic neutral axis is given, and due to elastic and plastic, the strain and stress behavior shown here. Now if we see here, first row, in the first row, if we see elastic behavior, it means strain is less than at strain at yield point. See here, as I have told you, up to the elastic point there is no strain. It means strain is there, but very less amount of strain is there, but stress is increases. Up to the elastic limit, strain is increases. So here strain is less in the elastic, or strain is equal to the yield strain at up to the yield point. Whatever strain is there, that is equal to the regular strain. But if we compare this to stress in the elastic behavior, if we compare strain to the stress, so here stress is a greater or more amount of stress is there. Stress is less than sigma y. It means sigma stress at yield or stress is equal to stress at yield. So this is the strain and stress. Now in the elastoplastic behavior. So next is the elastoplastic. It means your member will change its properties from elastic to plastic. After the yield point, your member change its properties from elastic to plastic. At that time, what happened? If you see here, at that time, your strain is increases than the elastic strain. See, in the elastoplastic zone, it means your member is going from elastic to plastic zone. At that time, strain is increases. And here, see now, this is very important. Stress is constant. It means whatever stress is increases, that stress is increases up to the yield point only. Yield point पर्यंतच तुमची stress increase होत असते. After the yield point, when your member goes on the plastic zone, so only strain is increases and stress is a constant. Upper side behavior is showing the strain and lower side behavior is showing of stress. So stress is constant after the yield point and strain is increases in the elastoplastic. Again you can see it. Now fully plastic. Now elasticity, it means member cannot carry the now elastic property of member is over, strain hardening. Elastic property of member is over. At that time, again strain is increases more than the yield strain, and this is the behavior. And at that time, your neutral axis is shifted at a plastic neutral axis. See here at center, here at center. Now strain is increases, your neutral axis is shifted below. Again strain is increases, your neutral axis is shifted below. And at the failure, this is the failure point, this is the your plastic neutral axis. See, elastic neutral axis and plastic neutral axis कधी असतो तो किंवा behavior कधी change होतं? When your member under loading condition and the member goes from the elastic to plastic zone, plastic to full plastic zone, at that time plastic neutral axis is there, and at this plastic neutral axis your member will collapse. And again here stress is constant. Stress is a constant. It means no rotation, no alpha in this stress condition. Here alpha is there, here theta is there. So are you getting elastic and plastic behavior of this cross section? Elastic behavior of cross section means strain is less or constant up to the yield point and stress is increases. After the yield point, stress is decreases. It means stress is constant. Plastic झोन मध्ये ज्यावेळी तुमचा मेंबर जातो त्यावेळी काय होतंय, स्ट्रेस कॉन्स्टंट राहतोय आणि स्ट्रेस इन्क्रीज होत जाते. सो दिस इज द behavior of cross section, stress strain behavior of the cross section. Again here shown behavior of the movement also. In the last slide we have seen stress and strain behavior, but here we are showing the movement curvature relation. So if we see here, movement and rotation means movement curvature relations. So here MP at the yield point, up to the yield point, whatever stress is generated, due to that stress, the my sigma at the sigma y, it means at yield point, sigma y is nothing but stress at yield point. Similarly, my is nothing but moment at yield point. What is m? Moment. How to calculate moment? M is equal to what? So here sigma by y. So whatever stress is generated at how much depth is nothing but your moment. So at this stage, for this particular depth, moment is my generated. If the member is in the plastic zone, whatever stress at plastic zone divided by depth of this particular member is nothing but the plastic. So here MP and My. So My is the movement at yield point and MP is a movement at plastic zone. So this is the behavior depends on the, now here theta is there. Alpha means theta is there. Alpha is less than 1. But here alpha is 0 when stress is a constant. At the constant stress, alpha is 0 and the stress is varying. At that time, your rotation is a changes. So we have seen in the theoretical part while learning the design of steel structure subject. So these are the rotations we have seen. And due to these rotations here, moment capacity is there. So this is the moment curvature relationship. If theta increases, your moment is increases. If theta is 0, then your moment will be the constant. So again here, depends upon the strain condition and stress condition, the moment curvature relation is shown here. Okay. So now next point is the plastic hinge. In the behavior of cross section, initially we have seen the stress strain relation, then we have seen the moment curvature relation, and third we are seeing here plastic hinge. That is the behavior of this particular member. Now, what is plastic hinge? So in the idealized moment rotation curve, the cross section is a linearly sustained movement up to the plastic movement capacity of the section, and then yield in rotation an indeterminate amount. What will happen? Your member after the elastic limit goes on the plastic zone. At that time, the linear variation, linear sustained movement up to the plastic movement capacity. Plastic movement capacity at what point plastic movement is greater? So this is the your necking point. It means ultimate load is there. So at that ultimate load, your plastic movement capacity is reached. Highest plastic movement capacity is here. And this is the My. And this is the your MP. So My is at yield point and MP is at ultimate point. So that behavior is we can show by the changing the cross section. Again, to use this idealized, the actual section must be capable to sustaining the large rotation. That is must be ductile. It means what? When your member under in the loading condition in the plastic zone, so more ductile and ductile your member. It means more strain is there, more elongation is there in this particular member. Ductility is increases in the plastic zone and member going to the failure. मेंबर आहे लोड घेतोय 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 कुठेपर्यंत घेणार आहे तो तुटेपर्यंत पण तुटायच्या अगोदर तो काय करतोय स्वतःला इलॉंगेट करतोय फुल्ली स्ट्रेच इट मीन्स at that time strain is increases and members under the plastic condition. मग तुटायला ज्यावेळी जाणार आहे मेंबर at that time the capacity of member at the failure is a formation of hinge. ज्यावेळी तुटायला जाणार आहे त्यावेळी काय होणार आहे तिथली त्याची स्ट्रेन कॅरी करण्याची स्ट्रेस कॅरी करण्याची कॅपॅसिटी डिक्रीज होणार आहे. It will decrease the capacity of strain carry and it will rotate. If we take the example of one small bar that is we are calling as a तार, आपण एक तार म्हणतो, बाइंडिंग करायची स्टील वायर बाइंडिंग करायची तार बघितली सर्वांनी. So if we rotate, if we hold into hand and at one place if we rotate or elongate, so one location is there that की तार आहे ती कशी पण कुठेही मूवमेंट होते ना त्याची एका पॉइंट मधून. So that is nothing but the formation of hinge. So similarly all the structural element, all the structural cross sections having such capacity at one location when we apply the load more and more. Then once plastic moments capacity is reached, it means strain carry करण्याची capacity reach होईल, maximum होईल. At that time what will happen? The hinge will form. Am I audible? Okay, so now we are telling about the plastic movement capacity. So the plastic movement capacity is reached at the point where your member will be the collapse, and at that point if the plastic moment capacity of member is reached, at that time the formation of hinges. So this term as a plastic hinge at and it is basis on the plastic analysis. So when plastic hinge occur, when your plastic movement capacity is reached and your section can rotate freely, it means behave a hinge. You have seen our home entrance door, so we can close and open the door. So it means at the supports we have provided the hinges. It means rotation capacity is there. Similarly, when any steel structural member under loading condition at the final stage of collapse, there may be a fully plastic moment capacity is there and your member freely rotate. It means behave like a hinge, and that capacity we called as, or that term we called as a plastic hinge. And at the plastic hinge, stresses remains constant, but strain, hence rotation can increases. It means again strain is increases, but stress is a constant. So that is the plastic hinge. So when plastic hinge form, or where plastic hinge form, that we have seen here. So now, so while the plastic analysis, there are so many assumptions are there. So what are these assumptions? So these assumptions are the material obeys Hooke's law until the stresses reaches the yield value and thereafter remains constant. What is first assumptions we have to consider? That material obeys Hooke's law. It means what? Hooke's law is nothing but stress is directly proportional to strain. It means that is the elastic condition. So that is the first assumptions we have to keep in mind. Then the yield stress and modulus of elasticity have same value in compression and in tension. So material is of one material, material is having modulus of elasticity. So that modulus of elasticity is we have to keep constant. It means still having modulus of elasticity is equal to how much? 2 into 10 raised to 5. 2 into 10 raised to 5 is the modulus of elasticity that we have to keep constant when your member is under tension and compression. Are you getting? Then the material is homogeneous and isotropic in both the elastic and plastic state. Homogeneous and isotropic. It means what? The material is made up of at one time. No joint is provided for this member. Whatever member we are testing or we are giving the load on this member, the material is homogeneous. Steel rod is homogeneous. It means in industry, we are made up of the steel bar of 20-meter length. We are keeping the lab in the construction, that is another part. But when we are testing this particular rod, at that time that rod is a homogeneous. 20 मीटर पैकी 1 मीटरचा तुकडा काढूनच आपण तो UTM मध्ये टेस्ट करतो स्टील रॉडचा. At that time that 1 meter piece is a homogeneous. This is not a lapped bar. It means that assumptions we have to consider while analyzing the plastic behavior. The member is a homogeneous and isotropic. Then the plane transverse section remain plane and normal to the longitudinal axis of bending. As we have seen this also, your plane of section is a transverse and it is remains plane and normal to the longitudinal axis after the bending. That assumptions also we have seen in the analysis of beam in the structural mechanics also. Then there is a no resultant axial force on the beam. On the beam, no resultant axial force. That assumptions we have to keep in mind. Then the cross section of beam is symmetrical about an axis through its centroid parallel to the plane of bending. The cross section is a symmetric. We have to provide the symmetric throughout the vertical axis or centroidal axis of plane of bending. That is one of the assumptions we have to keep in mind. And every layer of the material is free to expand and contract longitudinally and laterally under the stress as separated for the other layers. So every layer of material is free to expand and contract longitudinally and laterally of the stress. If the material is homogeneous, then it will expand and contract longitudinally and laterally under the stress. So these are the assumptions of the we have to keep in mind while analyzing the plastic behavior. Okay. So now, what behavior numerically we can see? So, if we see here, we have taken the example of this cross section. So here elastic and plastic. So we are analyzing the steel structural member. So elastic analysis we have to do here now and plastic analysis. Analysis means what? From since plus first slide, we are talking about the plastic analysis of the steel structure. Right? We are analyzing means what? We are the measuring the stress, strain, moment, and collapse load that we are measuring. So now how to measure? So now here elastic behavior. So this is the your cross section. If you see, this is the cross section. So now here YT and YB. So CG means depth of neutral axis. This is the neutral axis, elastic neutral axis. So YT is the depth of neutral axis from top and YB is the depth of neutral axis from bottom. This cross section having some area and CG of this area is here and CG which is from the depth of YT and from top and from bottom at YB distance. So here stress is equal to stress at yield or stress is less than at yield stress. So this is the, in this area compression is there, in this area tension is there. At top compression is there, at bottom tension is there. So this is the elastic behavior we have shown. So similarly we can go for the plastic behavior here. Now again here same cross section is there. Now in the plastic zone, the depth of neutral axis is shifted below, as we have seen. See, this is the depth of neutral axis and this is the now depth plastic neutral axis. So here elastic neutral axis and here plastic neutral axis. So plastic neutral axis is shifted below. Why? We have seen when the strain is increases in the member, then your plastic neutral axis is shifted below. So this is the plastic neutral axis. So again, now here we have shown the variation is in linear variation. We have shown here linear variation and here we are showing the variation is a constant. See, variation of the stress is a constant here and here variation of stress is a linear. It means in the elastic, the stress is in the elastic behavior, stress is taken or stress is increases, and in the plastic behavior stress is a constant, only strain is increases. So here behavior is shown here. So now this compression area and this is the tension area. So the CG of this compression area is here and CG of tension area is here. It means this is AC. AC is nothing but area in compression and AT is nothing but here AT is written, that AT is nothing but the area in tension. So now again here this compression area and tension area is divided by the CG. So main CG of whole area is here, that is plastic neutral axis, and again compression area and tension area. So CG of compression area is located here and CG of tension area is located here. So this is the behavior of the of this particular cross section in elastic and plastic. Now see, in elastic the compression and tensile area is compression and tensile force is the same. Again in the plastic also compression and tensile force is same. It means when member under loading condition, how much force is generated in compression, that much force is generated in tension also. Similarly in the elastic and plastic. So C is equal to T is nothing but what? Force in compression is equal to force in tension. हे ज्यावेळी असेल त्यावेळीच तुमचा हा मेंबर स्टेबल आहे. जर टेन्साइल फोर्स जास्त होतोय कॉम्प्रेशन फोर्स कमी आहे असं होत नाहीये तुमचं बिहेवियर ज्यावेळी आपण टेस्ट करतोय तेव्हा. बिकॉज द लोड इज अप्लाइड ऑन द सेम अमाउंट. टेन्साइल फोर्स असो किंवा कॉम्प्रेसिव्ह फोर्स असो, द लोड इज अप्लाइड ऑन द सेम अमाउंट. देयर मे बी चेंज इन एरिया बट द amount of load is the same of tension and compression. So C is equal to T. So now here area in compression. So initially first we will see the elastic behavior or elastic analysis and then we will see the plastic analysis. Okay, now C is equal to T. Now here my it means movement at yield point. Elastic behavior पाहतोय म्हणजेच yield point पर्यंतच analysis करणार. प्लास्टिक analysis करतोय म्हणजेच काय, yield point नंतरच जे काय behavior आहे त्याचं analysis करणार. So very clearly you can see here elastic and plastic. So up to the yield point my, after the yield point mp. Up to the yield point sigma y, after the yield point sigma u, ultimate load. So similarly here my is nothing but here sigma y into I by y. So as we discussed, moment is equal to काय असतंय, stress into here I by y. So here moment is equal to at yield point sigma into I by y. So I by y is nothing but here Z. So ZE, why written here ZE? E is nothing but the elastic. So my is equal to sigma y into ZE. And here my is the yield moment and ZE is the elastic. Here ZE is the elastic section modulus and my is the yield moment. So this is in the elastic. So here our session will close. Join again.